I want to talk about Alaska as a spaceport, and in particular I want to focus on Poker Flat Research Range and Kodiak Launch Complex. Now these aren't really spaceports, they're more like launch complexes. But there's some real opportunities here and some exciting things for both research, education, and for the state of Alaska. So to start off, I thought I'd start with a picture of the state of Alaska. Before coming here, I heard the word vast. And I wonder why that word vast. Having been here a few months, I finally get it. I understand why that's about the only word you can use is vast. It's an enormous state. It's the last frontier, and this talk is sort of where the last frontier meets the final frontier. If you're a Star Trek fan, but for a geophysicist or a space physicist, it's an incredibly exciting place. And just to run through some of the things that you all know that goes on here, there's a lot of volcanoes. I understand in the lower 48. There's a volcanic eruption about every 20 years. But here in the state of Alaska, there's a volcano erupting about every 6 months. So that's why we have the Alaska Volcano Observatory and a whole volcanology group. Earthquakes. This is a very exciting place seismically, and a lot of stuff goes on here, a lot of opportunities to study how the earth shakes. Tsunamis related to earthquakes, and on a more serene scale, glaciers. Lots of glaciers, lots of activity and the effects of global change. Permafrost. I didn't know much about permafrost before coming here, but now having traveled around the state and seen all the difficulties of building, how things sink into the ground if you're not careful with permafrost, this is pretty exciting. Ice and snow. We have a snow, ice, and permafrost group. This is actually a photograph of Annie Mahoney, who was out at helping the Rinda and the Healy bring oil to Nome. This is one of the photographs from that expedition a few weeks ago. Tectonics and sedimentation, lots of mountains and lots of erosion around here. Extreme weather, especially here in Fairbanks, and I'll be talking a little bit about that. And then finally the Aurora, space physics. So all this exciting geophysical activity happens right here in this one state. It's pretty amazing. And one of the great things about the Geophysical Institute is that we pretty much cover all that stuff. I'm sure all of you are aware of where we are on campus. It's the LV building, this large block building with the big antenna on top. And if you look at our logo, most of what I just talked about, volcanoes, volcanology, earthquakes, it's all extreme weather, it's all in this nice logo. So what I want to talk about for a second, in the Geophysical Institute, we're divided into groups. We have 8 groups that study all these different phenomena. We have a volcanology group that studies volcanism, seismology, and focuses on volcanic hazards. We have a Alaska Volcano Observatory, which actually goes when there's a volcano and a risk of ash that can interfere with aircraft, goes into operational mode in partnership with the USGS and the state DGGS. We have a seismology group that studies earthquakes, tsunamis, and a lot of paleoseismology and lots of related phenomenology. As I mentioned, we have a snow, ice, and permafrost group that studies glaciers and permafrost. When I hear what it's like to be a student here, to go out in the summer and sit on a glacier, camp out, and make radar measurements, I'm jealous. Some of the opportunities here for students to get out in the field and do some really exciting stuff in a very exciting places is terrific. Tectonics and sedimentation. Atmospheric science. This image has become very real to me, until I guess all of us here. I was riding with somebody to the airport a few weeks ago when it was minus 51, and he goes, "You can taste the air. It's kind of chewy." But we have in the institute, we have a whole group and several people who are actually studying the physics of this very unique laboratory we have here in Fairbanks. And hopefully something good will come out of it. These guys study everything from the boundary layer and lower and up into the middle atmosphere. And this is actually a shot of a LiDAR, a laser, out at Poker Flats going up to sample the upper atmosphere, the middle atmosphere, up into the upper atmosphere. And finally, space physics and astronomy. I'm an astronomer. That's my background, space physics. But we study space physics, magnetospheric physics, solar physics. And a couple of new disciplines down here near the bottom are high altitude lightning. This is lightning that goes up to from cloud top up into the bottom of the ionosphere. A new phenomenon, new the last 10 years, but The Geophysical Institute at the University of Alaska has become one of the leaders in this field of study, and also infrasound. And infrasound spans many disciplines. Education is extremely important, and there's a great opportunity here in the Institute to do education, to reach out into the state, and I think education is one of a number of growing areas within the Institute, and I'll be coming back to this, especially as it relates to space. Remote sensing, another growing area. Andy Mahoney was actually out of the remote sensing group who went out to Nome to sample the ice, along with Greg Walker. I think Greg gave a talk here a couple science lectures back. And we even have a small but maybe growing planetary studies group here in that discipline. So shifting back to space and the spaceports, I want to talk about our Poker Flat research range. I heard somebody a minute ago talk about rockets and space going into orbit or suborbital. And just a quick rule of thumb for you, if you're not a rocket scientist, we stack motors together, 2 to 4 motors, and we launch payloads or satellites. If we can achieve a velocity, it's all about speed. If you can get the speed up to about 7 kilometers a second, which is about 4 miles per second, then you can achieve orbit. If you don't get to that kind of a speed, then it'll come back down again. So at Poker, the rockets are typically about 17-inch diameter, stacked in 2s up to 4, and they go up to 300 kilometers, a couple hundred miles, sometimes out to 600 miles up. But usually, well, you can't go into orbit from Poker because the rockets aren't big enough. And as I'll talk about in a second, whenever we launch something, the first, second, and third stage come back down again. And so that has to be carefully planned so they don't come back down someplace bad. So we can't launch satellites out of Poker, but we can launch sounding rockets. I was actually here in the 90s launching a NASA sounding rocket. And what you see here, this is out at Poker showing some of the launch rails. These are rockets. You can see the fins sticking out of the side of this. This is styrofoam. At Poker, they encapsulate the rockets in styrofoam, and at the bottom, they pump in heat to keep them warm. You want your scientific payload to stay warm, but you also want the rocket motors to stay warm so they don't crack and fail. So this is typical. They launch it just slices right through the styrofoam. There's usually burned styrofoam out there that students come back later and pick up in the spring when it warms up. But I'm starting with sounding rockets because it's a terrific way. That's how I got my start. My career as an astrogeophysicist was building and flying a sounding rocket. What's great about it, it's short time scale. You can conceive of an experiment, you can build it, you can assemble it, test it, launch it. The experiment only lasts 10 to 20 minutes. Get the data, analyze it, and get a degree out of it. So many times, and I'll be coming back to this more and more, Chancellor Rogers mentioned it, so many times space has become so expensive and it takes so long that it's hard for a student to get more than just a small part of a big program. And that turns a lot of students off. We're not doing as many sounding rockets as we used to, and that's an issue. But we are doing sounding rockets. And the exciting news is that last Saturday we launched a rocket. This is actually out of the news minor. If you look on the front page of the paper day, if you haven't gotten home yet, there's actually a photograph of the sounding rocket that launched out of Poker. It's a great success. They nailed the Aurora. There's also a CNN website. I don't want to click on it because it takes a while. I think you have to sit through a Priceline commercial. But when you get home, and this is too hard to cut and paste. But maybe at the end I'll click on it and see what happens. But it was actually on CNN. They talk about launching a rocket into the Aurora. I got a few more pictures here. They're absolutely spectacular. I think a lot of you probably saw the Aurora Saturday and Sunday, and it was Saturday's Aurora that we launched the rocket into. NASA did. So here's some photographs from that. Let me start up here in the top left. This is the sounding rocket payload. The primary institution was Cornell. Cornell University was the principal investigator for this experiment. But you can see other universities like us, here at the University of Alaska, Dartmouth, SRI, University of New Hampshire, and University of Oslo. This is a fairly sophisticated payload, and it comes in 2 pieces. It actually separated into 2 chunks and made measurements as it flew along. This is what it looks like on the rail. This is a 17-inch skin. This is a Black Brant 9, what's called. This payload weighed about 600 kilograms, and it went through an apogee, the highest altitude of about 320 kilometers. The payload came down about 200 miles uprange. You can see it's being assembled on the rail, and they're putting those styrofoam boxes. They haven't quite finished here. Here's a photograph taken Saturday night about 8:40. Mark Condi, one of our scientists from the GI, took this photograph. You can see the first stage lighting and going up. It shuts off about there. It continues to burn a little bit, and a really spectacular aurora. The aurora was really bright. It was north of us, moved south, and the PI from Cornell, he had to launch into it, so we had to wait. Then the aurora turned around. It doesn't usually do this, but it went back north again. So he nailed it. We were holding it T-minus 2 minutes. It takes 5 minutes to get to apogee, so he had 7 minutes he had to plan it just right, and he did a fabulous job. Got a couple more photographs. Here's one showing the 2 stages, showing the rail in the background, the first stage burning out, going through a little parabola and coming back down. I watched it till it hits the ground, and it was a big bright burst of light, and it disappeared. It must have exploded and then buried itself in the snowbank. And then the second stage, it coasted for a while. The second stage lit, the black band, and went on up. It burns out, and then the payload coasted up to 320, about 200 miles apogee, and it went on out. Here's another picture taken by somebody Saturday night of the aurora. It was really, really spectacular. Here's one more photograph. This is my favorite. This is an all-sky camera. It's looking up. It's kind of a fisheye lens. You can see the whole sky. So you can see in this photograph the aurora here and overhead, and then the rocket covered up. This is actually near the gate out at Poker. So this is really exciting. It's hard to describe what it's like. People spend several years of their lives getting ready for this event. There's several scientists. There's a lot of ground-based measurements. Our scientists at the Geophysical Institute support this with interferometers, with all-sky cameras. We had scientists downrange at Fort Yukon. It's a very closely coordinated effort. There's about 70 people there out at Poker to make all this success. The bad news about all this is that this is it for the year, one launch. As you notice, auroras begin to pick up. The sun goes through an 11-year solar cycle, and it'll be at a maximum next year. So the good news is we're going to be seeing more and more aurora over the next year, especially at night, especially when it's dark out, up through like March or so. But what's happened is these sounding rockets have become so sophisticated. You saw that payload. There's 9 or 10 experiments on this one payload. It takes a while. It gets expensive. And so we're not flying as many rockets as we should. And so the time scale and the opportunity to get involved is not there. So Mark Condi and Jeff Rothman proposed to NASA a way to maybe speed this up. And part of it has to do with NASA's concern that things aren't quite ready for prime time. NASA has become a little risk adverse. So Mark said, hey, what if we build a tiny rocket, a small rocket, that won't go very high, maybe just to 4 kilometers, a couple miles up. We can simulate a lot of the same things. It'll be microgravity, it'll be high acceleration. We can get into space. We can stack these things up. And so he's gotten some funding to proceed with that, and we're building these things in the Geophysical Institute. Here's an example of this little rocket. I have a movie that Mark gave me. This movie is filmed with a very high-speed camera, so it's going really fast, but it looks very slow. You can see the rocket ignite. There's no fins on this rocket, so you see the spiral here. We have to spin it for stability. So there are little rollers that fit in these helical tracks. So in this little thing, it looks like it's barely moving. It's actually moving pretty fast. It comes out, and I'll let the movie run a bit. It spins up. But the whole idea is to try to take some of the risk out to make NASA a little more comfortable, so we can actually move ahead. That new ideas, new concepts for experiments don't get rejected because they're out of hand because they're deemed to be too risky. So this is an innovation that I hope will help with this. But I'm a little worried the next year or so, even as we go to solar maximum, there won't be that many sounding rockets, onesies or twosies here at Poker, and that's a shame. Okay, now let me shift to satellites and back to Alaska and back to volcanoes. I want to talk about what you can do from space and how that helps the state and how that helps the scientists here in the GI. So I've got some examples of imagery from satellites. The first is just a visible image. As you can imagine, for detecting volcanoes and seeing the volcanic plume, this is a very valuable way to do this. I will talk about in a minute about our Alaska satellite facility, but this is data that was downloaded there. Here's infrared imagery. This is an image called 1,000 Smokes, and you can see smoke from the campfires, smoke from forest fires, in hot regions thermally. And this all works as long as there's no clouds. You got to have a cloud free for these visible infrared images to work. But if there's clouds, what do you do? And the answer is radar. Radar can see through clouds. And so what we do from space is synthetic aperture radar. This is an example on the left of one of the Aleutian Islands, and on the right, another synthetic aperture radar image showing the fresh ejecta coming from, and lava coming from these craters. These satellites aren't cheap, and it takes a while to get them up there. And the U.S. right now doesn't fly any synthetic aperture radar satellites. These are all done by some other nation, and I'm going to come back to this at the end. Another kind of SAR is INSAR. If you look here on the right, if you take two images at two different times, and there's been some change, then you can take the two images and line them up and create an interferogram, and what you see is change. In this case, as part of the volcano is risen, you see that the color changes. So it gives you an idea of what's happening. You can see magma flows and tilts. If there's pressure building up, that might lead to an earthquake. By taking two images with INSAR, you can actually detect this. This is a very valuable tool and very useful in Alaska. Hyperspectral imagery. Typically, when you see an image from space of the Earth, like what you see here, it uses three colors: red, blue, green, or something like that. Some combination. But some instruments use not just three colors, but maybe 100 colors, or maybe 1,000 colors. And when you do that, you get a great deal more information. You can actually distill a lot of products, a lot more information out of that image than you can from just the three colors. And I'll give you some examples. In my last job, before coming here, we flew a hyperspectral sensor, and I'll show you some of that in a second. So here's the other spaceport. This is the Kodiak Launch Complex down in Kodiak that's run by Alaska Aerospace Corporation, a state-owned corporation. It's an absolutely fabulous facility. In my last job, one of the last things I did was launch a satellite out of this facility. I funded the Naval Research Lab to build a satellite, communication satellite. The guys who went down there were astounded by what a terrific place this is. It's got a great location right here in Kodiak, and you can see you can launch south over this wide angle from about 110 degrees azimuth to 220. Last September, and I'll show you this in a minute, we launched a satellite came just on along the edge of California and down to Chile before going into a circular orbit, and then we boosted it up into a very high orbit, and that has some real applications for Alaska. So let me talk for a second about the Alaska satellite facility, and there's a bunch of brochures in the back corner back there. It's located here in Fairbanks, and this big dish on top of the LV building represents half of their capability for sensing, and they do quite a bit of image processing. This image on the bottom left shows what the view is out to the horizon from LV and from another place just off in the woods. I'll show you in a second. So you can see from right about here, you can see quite a large expanse. And if you look at polar orbiting satellites, these are a bunch of examples of polar orbiting satellites. And this is my best attempt to make that same circle. This circle intercepts most of those arcs. So what it means is that most polar orbiting satellites will fly overhead. And so the Alaska Satellite Facility can connect to them and download the data. And that's what they do, and they've been doing a good job of that for quite a while. Here's a quick list of some of the recent and current satellites that they're connecting with, NASA satellites and other satellites, and downloading data. And here's the two antennas again. There's one right here on top of the LV building and one nearby in the woods that are doing this. And this could be, this in conjunction with the things I'm going to talk about in a second are important now, but really important for the future. So let me go back to, Chancellor Rogers said my passion is for making space cheaper and quicker. For 30 years I worked for the Navy, funding space research and performing space research. And what I always heard, I put in quotes, that it just takes too long and costs too much. And the rule of thumb I had working in the DoD, and it's also true at other locations, is that a new space system costs about $1 billion, takes about 10 years. Sometimes it costs $10 billion, and sometimes it never makes it. You look around the weather satellites, the defense weather satellite system has been canceled because it's over budget. The INPOS weather satellite system went through about $7 or $8 billion and it was canceled. It's a real problem. In fact, one of my last jobs that Chancellor Rogers mentioned was with the Operational Responsive Space Office. Congress created this office in Albuquerque. It was Army, Navy, Air Force, NASA, NGA, NRO, and National Security Agency. And it was focused on how do you make space lower cost and faster, because it's just not working at these costs. Even NASA, they launched 2 years ago the SDO, the Solar Dynamics Observatory. It's a great success. It's sitting out there imaging the sun, but it cost $800 million. That's just really expensive. So what we were working on, and what's been my passion, is to try to drive the cost down. And here's some simple solutions. One is go small. And if you were here earlier, you saw Denise's talk about CubeSats. I'll come to that in a second. That's one way. Make them small and make them low cost so that students can build them, high schools can build these satellites. I'll talk more about that. The second thing is, this is something that I did when I worked with the Navy, is go simple. You saw that sounding rocket payload. It was so sophisticated. It had to have multiple measurements and backup and redundant instruments. And what happens is you get caught in a spiral of cost and schedule. It's got to be right. You got to make sure. It takes longer. The costs increase. And you work in the spiral, and sometimes it never comes out the other end. Things get canceled. I've been involved with several programs that were canceled. And the final thing I want to talk about at the end is cheaper rockets. Rockets are way too expensive, and there's a couple of initiatives on the horizon that could drive this down. But it's all about risk. We've become very risk adverse in both sounding rockets and in satellites, and it's taken too long and it's costing too much. So let me talk about small satellites. This is a bit of an echo of what Denise was just talking about. But imagine satellites that could fit in your hand. These were developed, the concept came from Cal Poly to make a standard size. It's 4 inches, 1 kilogram, 2 pounds. And I used to be kind of skeptical of what these were good for. I know they're great for students because you can actually build one in a short amount of time and do some things in it. People would ask me, what good are these CubeSats? And I'd say, well, they're good for students. And I actually funded the Naval Observatory, who built 5 of these little CubeSats and launched them in space. But the National Science Foundation got involved in this and started throwing out to the scientific community, what can you do with the CubeSat? And if you throw the idea out there long enough, some surprising ideas are coming out. The National Science Foundation has launched a couple, they're going to launch several more. So my idea of what you can do is changing. I don't know what you can do. I mean, who knows what you can do with these little satellites. You're a little limited with a 4-inch cube because you have to collect sunlight. We cover these with solar cells, and they're only 4 inches cube. You can only gather so much energy. But you can scale them. In the CubeSat community, they call this a 1U. This is a 1U. This is a 1U, 1.5, a 2U, and a 3U. This is actually a pretty popular size. These are called pico satellites, and these now are verging on the next size up, which would be a nano satellite. And there's quite a bit of, this has become a sweet spot. I don't know how many CubeSats or nanosats have been built in the last 5 years, but my guess is probably a couple hundred. You can actually order the parts online. You can build your own satellite for a few $1,000s now. And there's a lot of things to go into it, and Denise gave me some things, I'll talk about that in a second. But what's happened is a lot of the major rocket manufacturers and the DoD have decided these CubeSats, they're fairly benign. You can stack them in threes and put them in this little box called a Peapod, which stands for Poly, for Cal Poly, and Picosat Orbital Deployer. It looks like a loaf of bread, and it has a latch at one side, and you slide 3 1U satellites in it, or you slide 1 3U satellite in. You latch it, go on, put it on a rocket, as Denise said, put it usually down near the rocket motor, so it's not in anybody's way. You launch it. Let the primary satellite do whatever it's going to do, because they don't want to muck with you guys. They don't want to have you get in their way. So they launch, they push away and go do what they're going to do. And then when it's all clear, they pop this door and a spring pushes these things out. Now, some of my colleagues call these space debris because they're small. But they are getting more and more capable, and it is kind of important that you don't launch them too high because you don't want them to stay up there very long. So typically 500 kilometers, if you're at 500 kilometers orbit or less, the drag is significant, and you'll come down in weeks or months or a year. The shuttle, the station itself is at 400 kilometers, and it has to keep boosting itself up because there's quite a bit of drag. So as long as you don't go to 600 or 700, 800 kilometers without a way to come back down, then it will come down again. So you can do an experiment for months or a year or even a couple years and then come back down. But these are getting increasingly capable. And just an example, this is also something we did in my last job. Working with NASA Ames, we launched a CubeSat that actually deployed a 10-foot solar cell. You can hardly see the satellite in there, tiny little thing in the middle, and it deploys out in about 5 seconds. It was quite impressive. The first one of these we launched, it went in the ocean, the rocket did, but the second one was successful, and it actually got up there. This could be very important for small satellites to increase their drag so they come back down again. In 1989, NORAD tracked about 3,000 targets, satellites, and debris. There's been a couple of collisions in the last couple of years, and now they're tracking 19,000 targets. So a few more collisions, this number could go way up. So putting these solar cells to pop out a big 10 by 10 foot sail, it would increase the drag and bring it down. Another innovation we did in my last job working with NASA Ames was develop this wafer-like thing. It weighs about 80 kilograms, about 160 pounds, and it has slots, about 8 slots, to put a 3U CubeSat on the side. You stack this on top of the rocket, and a rocket has surplus capacity, maybe an extra 100 kilograms or so it's not going to need. They often put concrete on it and fly concrete into space and let it come back down again. But if you put this on, then you could put in eight or so 3U CubeSats or 8 Peapods and do quite a bit of stuff. Like I said, National Science Foundation, the National Reconnaissance Office, various organizations are getting on the Peapod bandwagon and the CubeSat bandwagon. This is what Denise was just talking about. We here at the university are building a CubeSat. It's a 4-inch cube. It has an antenna. It has a imager. It has a communications system. It has an attitude control system, so it controls its attitude. A power system, a command and data handling system, so you can send commands, and an environmental data logger. All the functions that are in a big satellite, you can sit in a 4-inch cube in the palm of your hand. And at least for students, this is a technology demonstrator, but increasingly these satellites are becoming more and more powerful. It's hard to imagine where you're going, but if you think about the capability in an iPhone or a BlackBerry, it's pretty amazing what you can do, and I have no idea how capable these are going to be. The next size up, you get into nanosatellites, now you're getting a little more capable. We were working with the Army who wanted to take a telescope, a 10-inch Questar, the same thing you can buy online or buy in town here. 10-inch Questar, put it in a box about 25 pounds with the same, it needs a camera, it needs a starfield camera so it knows where it's pointing, it needs inertial measurement, a control, an IMU, but the idea, and a radio, just like that little CubeSat I just showed you. But now you can get imagery from low Earth orbit at about 1.5 meter resolution, which is pretty amazing. If you look at Landsat, which is about 20 meter resolution, this is quite a capability. The Army thinks they can build these for $1 million a copy, and the idea would be to launch them quickly whenever they need to. There are several people out there working on the concepts for cheap rockets that can lift something about this, 10 to 20 kilograms into orbit very quickly for a couple $1 million. Some of them from rocket deployed from an aircraft, and some launched from the ground. The Army was also working on power, increased power, fold-out solar. This is a 3U CubeSat, fold-out solar cells. They claim they can get 80 watts, which is quite a bit from a 3U CubeSat. That's been one of the limitations. Now I asked the same Army guys, okay, you get 80 watts. Bringing in power is one thing, but you have to, in space, you have to reach equilibrium where you just keep bringing in 80 watts, you'll just burn up. And it's hard to shed heat, you have to radiate. And so I asked them how they're going to radiate to space, and they hadn't really thought about that yet. So this is still on the drawing board. At the Naval Postgraduate School, they're working on a 6U concept to take a 3.5-inch Questar, which I actually have one of those myself, build it into 3U CubeSat, the same kind of capability. They think they can build that for less than $1 million in a CubeSat form, and at 500 kilometers orbit, get about 3 to 5 meters resolution. And that's also pretty amazing. So that's going small. Now let me talk about going simple. At the Office of Naval Research, in the Naval Research Lab, we had an interest in flying a hyperspectral imager. This is 150 wavelengths that try to do some things, and I'll show you in a second. The Naval Research Lab had tried several times to do this, went through quite a bit of money, and had programs canceled. They got too expensive, there was something missing, and they got canceled. So a final time, I went to the Naval Research Lab, I had a little bit of money, and I said, how cheaply could you do this? Forget the past, forget the way you normally do it. So they said, well, look, here's the cheapest thing we could do. We could take an airborne monochromator. We could take a spectrometer that has gratings and optics out of a UAV, the same kind of thing that Greg Walker talked about a couple weeks ago. We could take a laboratory camera. Now, this laboratory camera shouldn't be used in space because of radiation and outgassing and things like that. Space is pretty harmful and thermal. So they took these two things and they put them in a pressurized box. They put air in the box, about an atmosphere, and they put a fan in the box to circulate the air. They wanted to articulate the whole thing, so they put a rotary stage on the back of it, this thing here, which is rated for vacuum. It can sit in vacuum, and this rotary stage can torque this whole instrument around so the instrument can look down through this slit. And to control it, they use a laptop computer. So the parts to put this all together were $100,000. And it's airborne quality stuff, not space stuff. The Air Force and NASA came to us, and the Japanese, and said, hey, we can fly you to the space station. And people gave us a hard time saying, oh, you can never do that. And the NASA would never allow you to do this kind of stuff on the space station. But we went ahead with it anyway. They spent about 18 months from when I gave them money to building this instrument and completing it. They got through all the safety hoops. They built it into this carrier that was about the size of a refrigerator. It's about 1.5 meters by 33 by 34 inches. The instrument was called Hyperspectral Imager of the Coastal Ocean. They delivered it to Japan, launched it on a Japanese rocket, the H-2B rocket, September 10th, 2010. It took a week for that rocket to catch up with the space station. The Japanese on the station have the Japanese experiment module. It's this pressurized thing that astronauts can hang out in, and this unpressurized thing called the Japanese experiment module, the exposed facility. They grabbed this and docked it, and then reached in the side and pulled out these refrigerator-sized boxes. You can see it right here. There's a grappling fixture on top, and they just plug it right into this platform. The platform clamps on. It's got power, telemetry, even coolant if you want. You can get 3 kilowatts of power and video, all kinds of telemetry. It's pretty powerful. 18 months later, we actually had 2 instruments. One was a space weather sensor. That's this gold-looking thing in front. I say space weather. It was a bunch of ultraviolet cameras that were looking. The space station was flying away from us. It was looking aft behind the station and measuring glow from the upper atmosphere and the ionosphere, the same as that rocket did on Saturday night. The hyperspectral imager was on the bottom looking out through that little slit I showed you. Let me go back a slide. That little slit right here was this slit here. And you can see the little white dot. That's the instrument looking down. So it was delivered September 10th. It's been up there almost 3 years. It's been working fabulously. And we did it for a few percent of what we normally do, those kind of things. Let me show you some of the data. This is focused on the oceans. So it's mainly looking in the blue-green out into the infrared. So a single image, it's a push boom, so it measures a bunch of wavelengths and as it flies along. Each image is about 40 kilometers wide, that's across here, by 200 long. This image here is 3 colors. This is a typical red, blue, green kind of image. We took 3 of the 150 colors. But having 150 different colors, people can go through and generate products. So on the right, this is a map of the depth of the water. This is an image off of Korea. And you can see that this is early on. We launched it in September. Actually, it was September 2009. This was some of the first analysis. But a lot of this water is only about 1 meter deep. So you can actually measure the depth of the water in single pass from this hyperspectral instrument that costs just a couple $1 million. Here's another series of images just to give you a feel of the capability. This is an image off the Florida Keys. This is red, blue, green to sort of orient you. This is a product showing diver visibility. So divers know how far can you see into water. Out here it's obviously pretty clear water, and it gets murkier as you move in. Here's the depth, again the bathymetry in meters. And then this is what the land is like. Is it soft? Is it muddy? Is it sandy? this is something that would be very important here in Alaska for measuring resources and determining water content and hydrological conditions around the state. So I'm kind of excited about this capability because it shows that you can take airborne stuff, put it in a pressurized box, do it quickly, not cost an arm and a leg, and get it done. So I'd like to do more of this. So the space station is in an inclination of 51.5 degrees, and so I just thought, well, that's great for measuring the oceans, but it's not very good for Alaska. I've had discussions with our volcanology group, and this is my attempt to show this is the space station, and this is roughly the orbit. It just barely clips the Aleutians. But you can imagine now, as Denise mentioned, a volcano observing system on the space station. You could actually see volcanoes almost anywhere around the Aleutians. You can look out to the side and do this. So this might be a real capability. So we're exploring some concepts to try to build another instrument like this, or some other instrument. Maybe take some infrared cameras, like maybe the kind you see over there, put them in a pressurized box and fly them. Something we could do in less than a year or so. So I want to shift to the final thing, which is rockets. Working in the DoD, these were the workhorses that we used for these smaller satellites. The Minotaur 1, we launched 2 of these out of Wallops, Virginia. We launched them east out over the Atlantic. Minotaur 1s are really Minutemen. They're built. The last one we launched last July was 44 years old. It was solid rocket motors. They still work like a champ. And each one of these Minotaur 1s can lift 700 pounds to 400 miles in a polar orbit. What we launched out of Kodiak in September was the Minotaur 4. This is a peacekeeper. This is swords to plowshares. It's much more capable. It can lift 2,200 pounds to the same 400 miles. But these aren't really cheap. This one is about $30 million, even though it's that old. It's hard to imagine why it costs so much, and it's built 44 years ago, but that's a whole other story that I'll talk about later. But these are cheap compared to some of the other satellites. I had a discussion today with USGS, and they have to use Atlas V's, which can be 5 times this. But the University of Hawaii and Sandia are working on a cheaper rocket. It's going back to the sounding rocket technology, solid rocket motors. This is being built with congressional money at Hawaii and Sandia. It's a rail-launched rocket, very similar, same kind of concept to what you saw at Poker. You put this on the rail. The idea is you have the rail horizontal. There's a shed over the rail. You can bring this in, assemble these motors probably in a day, put it together, pull the shed back, erect, and launch. We used to do this a long time ago. Scout launchers, Scout rockets. We used to fly a lot of those, and we flew them, 300 of them all over the world. In the early days of the space program, we were responsive. We could do things quickly and fairly cheaply. The promise is this kind of a rocket can lift 300 kilograms, which is 600 pounds, to orbit for $10 million. And so hopefully by next year, this will be a reality. Hawaii is building this. We'll be building this in Kauai on the PMRF, the Pacific Missile Research Range, and then launching. I've had several discussions with the Alaska Aerospace Corporation. If we had this capability here in Kodiak, we could launch our own satellites, not on our own, not the GI, but in partnership with others. But I think this kind of a rocket has a great deal of potential to change the equation here in terms of cost and schedule. And I said it has a capability of 300 kilograms, and so what can you do for 300 kilograms? What's in that range? Orbcomm satellites that use for satellite radio, they weighed about 40 pounds each, 20 kilograms. The Navy is very interested in altimeter. The last one they launched, this is to measure the height of the oceans. Last one they launched weighed 300 kilograms. NASA launched out of Kodiak 2 years ago the FastSat, which weighed 90 kilograms. The Israelis, I showed you a SAR image. The Israelis have a SAR that weighs 260 kilograms. And there's several other SAR concepts to get it down to 100 kilograms. Imager, this is something the Brits have been building and flying. These are very low cost, and they're pretty lightweight. So in that class, 300 kilograms, there's a whole lot you can do along the lines of what I've been talking about. So let me finish up with one of my last, again, this is one of the last things I did working for the Navy. It was a spectacular morning at Kodiak. It was sunny, been sunny for several days. I guess that's rare. It was warm and bright. We launched this satellite, TACSAT 4. This is what it looked like. It had a 12-foot dish. This dish is about 12 foot side to side. And it was an UHF, ultra-high frequency communication satellite. And we were testing out other concepts for doing that. That satellite launched into an orbit from Kodiak that went up to an apogee of 12,000 kilometers. It's an ellipse. It goes up to 12,000 and down to about 600 to back up again. What that means is we were doing it back then primarily for Afghanistan, Central Command. And you're looking in green, it means that satellite would be over Afghanistan about 7 hours a day. And the concept was to show that one satellite would give you 7, but maybe if you did 3 or 4, you could get 24/7 over Afghanistan. But the real bonus is what you get in the Arctic. And there in the Arctic, you get about 10 hours a day. And so the Alaska Aerospace Corporation is talking to the Canadians and others about, this concept to launch, not out to launch to this kind of an altitude, 12,000 kilometers. 2 of these, if you had one up here and one down here, then one would come up and one goes down. And then all of a sudden you've got 24/7 over the Arctic. Your satellite dishes are pointing out at the equator at satellites that are out at 36,000 kilometers, quite a ways away. This is quite a bit lower, and there's a lot of radiation belts in between. So this could be a major enabler, and I hope they can do this. So to summarize, this is an exciting place to a geophysicist, a space physicist. Alaska is an incredibly exciting place. There's a whole lot we can do from space. Sounding rockets that go up and come back down, poke through the Aurora, and I'm really proud of what happened this last Saturday. But we need to cut the cost down, and we need to crank up the tempo. And the way to do that is to make it smaller, CubeSats, make it simpler, fly airborne stuff, take on more risk. And these lower cost rockets, air-launched small rockets or these other rockets are going to be important. I think we're incredibly lucky to have Poker Flat, to have the Kodiak Launch Complex and the Alaska satellite facility. And I think there's tremendous potential to put us all together and make Alaska really at the forefront of space research and space launch here in Alaska. And thanks for coming.